Hi, what I'd like to do with this video is review some information from the chapter on uh, sampling distributions and estimation and go walk through some concepts that I want to reemphasize out of that. I'd like to walk through how do you make it, what are these tests, z-tests and t-tests, a little bit more for you, and how do you select one? And then I would like to take a problem and walk through the problem so you have a sense about how I go about solving these problems with the tools I've given you here. So that's what this video is going to be about. Let me start here. Kind of a key first issue here is language. This chapter, more than any other, really focuses on the issue about the difference between a sample and a population. With samples, the two major measures that we're working with and this are means and standard deviations. And there's the bar X is for the symbol for a mean for a sample. S is typically the symbol used for standard deviation for a sample. But for a population, that's when you have all the possible cases of something, then the symbol we use for a mean is mu, and then the symbol we use for the standard deviation is sigma. And these are called population parameters, where they're the same things are called sample statistics. Why am I why introduce this level of complexity? Well, it's because there's different you can work with them differently. You have to work with them differently. With the population, we assume we have all the cases that are possible. Now, and for instance, if you want to say, what's the average height of a 40-year-old male? Well, the population is worldwide. There's probably roughly 4 billion, maybe only 2 billion adult males in the world. But the idea that somehow you're going to go measure every one of those to get an estimate of that what the population height is unrealistic. So what you do is you take a sample of some size, and from that sample you extrapolate to the population. And you can do that with different degrees of confidence. And the degree of confidence comes down to what's the likelihood you're willing to make an error? Well, that's alpha. Alpha is the indication of an error in something, a type 1 error. So what we're doing here is part of what this stuff is about is saying, how do you know something? Well, you collect some data. Well, how do you know whether or not your data is really biased or not? Well, this type of statistics is the type of work people do to say, well, here's how I can make a decision about some of that stuff. And here's the level of confidence that I have in my decision-making process. This is an extension of the stuff I started off with back when we talked about hypothesis testing, type 1 and type 2 errors. In this case, we have alpha is an indicator of a type 1 error, and we get a confidence interval based off of using alpha. Now, there's different kinds of sampling distributions that are used. And the sampling distributions provide a theoretical framework or conceptual foundation to some extent for making these leaps of inference with our numbers. There are three major, well, there's a lot more in this, but first of all, I'm not going to deal with looking at significant differences in standard deviations. There's a whole other place called analysis of variance that gets into that. That's a separate course or two, and we're not going to go there. I'm just trying to give you an overview of how this is done. And even these tests are used in a broader range I'm going to use them here. Here I'm going to use them strictly about estimation. There's a normal z-test. We've talked about a z-distribution before, and we talked about that first of all back when we started looking at continuous probability distributions. And the Z distribution is a continuous probability distribution. And we're trying to figure out, does something fall inside or outside that? There is an alternative to that, which is the T distribution. And T distributions start off with the assumption that you don't know what the population is. You don't have any way of estimating necessarily what some of the standard deviation or the mean of that population is. But you have a sample. From that, you're going to do some estimation and figure out with what degree of confidence can you do something. They started using, interesting little kind of side story here. The person who developed the T distribution used to work for a beer company, like in the name of it, an English beer. Anyway, and they used it as a way for trying to say, okay, is the hops level or something, as a measuring things, a quality measurement about their beer. And they realized, well, you don't know what the population is here. You're always working with a series of samples, and realized there's a problem with that. And the problem is we don't know necessarily what the distribution looks like. And for a lot of our estimation, we're assuming that we know what the underlying distribution is. We assume it's normally distributed. Anyway, there's two tests here, the Z test and the T test. I give you three different worksheets. And the question you have to look at is say, well, which one am I working with? First of all, if you're working with a proportion, and how do I know whether I'm working with a proportion? Well, if I say the average size of something is that I'm not working with proportion, I'm working with means. In that case, we'd be working down here, one of these two things. If I say to you, in fact, I'm going to come up with later, we're going to talk about the sand dollar problem. If I start off with sand dollars and I said, I collected 10 sand dollars and 4 of them had a purplish tint to them. What you got here is a proportion. 4 out of 10 have a purplish tint to them. Now, is that unusual? Well, compared to what we find normally on the island is, but a proportion usually starts with a percentage. And it's that usually it's typically when proportions are used with dichotomous data, whereas means are used with continuous or discrete data. When you're thinking about this stuff, it's like if something has a certain kind of error or they're bigger than something or they're missing something, how many are missing something? That's a proportion. Anytime you have a proportion, you're going to use the normal Z test and you're going to use it for proportions. That's one of the 3 choices for you. The other possibility is you have, in the sand dollar case, for instance, we have the average diameter of a sand dollar. Now that's a continuous variable. So we're talking about means. Well, there's 2 possibilities here, a T test or a normal Z test. There are some requirements for these things. And but the requirement for a T test is sigma is not known and is normally distributed. For using the Z test, sigma is known and is normally distributed. Now, the other possibility is, again, same thing, not known and n is greater than 30, or it's known and n is greater than 30. The difference between a T test and a Z test for looking at averages is, do you know sigma? When you look at problems, what you're going to try and figure out is, do I know the population standard deviation or not? And if I don't know it, then I've got to have to use a T test. If I know it, then I can use a Z test. That's the key thing. So it's really, you look at this chart and you kind of, well, this is really confusing. It really comes down to two questions. Do I have a proportion or do I have an average? And if it's proportion, it's like, well, there's only one test there for that. If it's an average, then the question is, do I know sigma or do I not know sigma? If I know sigma, then I'm going to use a Z test. If I don't know sigma, then I'm going to use a T test. That's the simple stuff we're going to be working with. I mean, It's really that simple making the choice. Now, let me just mention, real life, it gets more complicated than that because there are a host of other tests that are out there in this process. But for purpose of this class, given we've got a couple weeks left and we're done in it, and we're not going to go into all those other tests, for this in this context, that's the simple stuff you can pay attention to. And I'm trying to really focus on what I think is a key issue around these things. So, by the way, there's a quiz out there where I give you I think I do 5 problems. And I present you the problems and I say, okay, which test do you use? And you should be coming back to this chart, which is in was in last week's readings, and use this chart because that'll help you just sort of walk through which test to use. And I would suggest doing that quiz before you work on the problems this week. Okay, let me talk about a problem here. You're walking down a beach on your favorite island and collecting sand dollars. You find 9 of them, which have an average diameter of 4.72 centimeters. This seems smaller than usual. You do some research and find the average sand dollar diameter on the island is 5.02 centimeters, with a standard deviation of 0.7 centimeters. You wonder if these are significantly that's referred to your sample, are significantly smaller or at the 0.95 confidence level. So problem starting, we start with what do you know? First thing, sample size equals 9. Measuring, what are we measuring? We're measuring sample average diameter equals 4.72. And then it says you do some research and the average sand dollar of the island is 5.02, the standard deviation of 0.7 centimeters. In this case, it is legitimate to use the average for the island, what they say as your population average diameter equals 5.02. And population standard deviation, I can't see if I can do this here correctly. I want to insert a symbol equals 0.7. So you know some stuff here. I mean, first of all, we're going to go back up to my chart. Am I measuring a proportion or an average? Am I talking about average diameter? I'm clearly talking about an average. So I'm not using this one. I'm not working proportions here. Do I know sigma? On down here, I've pointed out the sigma, the standard deviation of the population. This is the average for all of them that they know about the island is 0.7. So that's the population standard deviation. So I'm working with an average and I know sigma, so I'm going to be using a normal Z. Oh, one more thing. I want 0.95 confidence level. Now that's going to become an issue. Just a little thing here. It's like what I'm looking for is 90 or 95% confident that the true value is within some limits here. that means there's a 5% possibility of an error. 95% of I'm pretty confident the true values in this 95%. I don't think it's in the outside 5%. So alpha, let's see, can I come up with alpha here? Nope, nope, let's go back. Undo that. Back to insert, symbol. Alpha equals 0.05. That again is 95% confidence true, 5% chance of an error. That's how you think about confidence intervals versus alphas. If you want to have a 99% confidence level, you'd have an alpha of 0.01. The confidence interval equals 1 minus alpha. Just something to keep remembering, because they're gonna ask this in different places. It's gonna come up. So, given that, I'm gonna take a step back here, and I'll come back and I'm gonna try and share something different. No, that's not what I want. Okay. So I'm looking at a worksheet here that is confidence interval for Z distribution. And this is with means as opposed to proportions. What's my alpha? 0.05. See, one of the things down here says 1 minus alpha is 0.95. Okay, it's giving you that stuff. What's the sample size is 9. Population standard deviation is 0.7. Now, you could go two ways here. You could either say, let's put in the confidence interval for the sample or the confidence interval for the population. And you can go either way. What we've done is with the sample size of 9, we know what the sample size is, so we can get some estimate of this thing. I'm going to put in the population, 5.02. And what it says to me is the confidence interval is 4.56 to 5.47. I'm going to count that as 4.6 to 5.5. Now, I got to go back and check again. I missed this along the way. I've forgotten it, quite frankly. What I have here is the average sample was 4.72. So that my sample is 4.72. That falls within that confidence interval. What that would say is, yeah, my sample's small, but it's not significantly smaller. Not of the estimate, what you could expect 95% of the time is the sample size, as long as you're using samples of 9, it's going to be between 4.6 and 5.5 inches. centimeters, I'm sorry. And we got 4.72. So we're within that interval. So no, my sample is not significantly different. Now I'm gonna switch some numbers here just to suppose instead of 9 here, I put my sample size as 90. Bang. Well, look at my confidence interval. It jumps to 4.9 to 5.2, and that's rounding up. If I'd had a sample of 90 and I got 4.72, my confidence interval would be much smaller. As sample sizes increase, confidence intervals get smaller because you can have more confidence. You can trust more in a large sample to be unbiased than you can in a small sample. Let me turn this back and say, suppose I was down like 45 here instead. I got 4.8, 5.2 again. It's a little bit larger, but, and even then, if I had 45, my sample size was 45 instead of 9, this would tell me, it's like, okay, this is unusual to have that size. Sample size and confidence intervals tend to go together to be, I would say, inversely related. I think that's true. The larger your sample size, the smaller your confidence interval. The smaller your alpha, the larger your confidence interval becomes. That's how I'd walk through the problem zone. That's the sort of process I would walk through for doing this. Now, I'm going to ask you some places here. You should pay attention to everything I'm asking you. Because part of the answer is, do I think this is significantly smaller at the 0.05, the 95% confidence level? And I'd say, no, I don't think it's significantly smaller at that confidence level. Now, if I asked you, well, if you didn't know, well, let me turn that around again the other way. One of the things I could do here, and let me go back and just note this. I want to share screen, go back here. Nope, wrong one. I guess the point I'm going to make here is I made a decision here to put in the population standard deviation. I could have put in the sample standard deviation, 4.72. With that, what I came up with, instead of these, clear all these things out. I get a 95% confidence level of 4.3 to 5.2. I'm using a different anchor point in this, which is the sample mean as opposed to population mean. But the population diameter is 5.08, I believe I've had. And that is within this distribution. So either way I come at it, the answer still comes up is, yep, if I work from the population mean, then the sample mean is within the 95% confidence interval. If I work from the sample mean, then the population mean is within, that's 95% confidence interval. That's as it should be. So when you say, I don't know which one of these to use, if you know them both, you can go either way. It really doesn't matter, because ultimately the question is, does the other one fall within that range or not? And as I demonstrate here, either way, it does fall within the range. So that's how to go about solving the problems. I would start off first with, I'd said, I start off with all my problems like this. So start write down first, what do I know? Then I'd go to the chart and say, okay, given what I know, which test should I be using here? And then pull up that correct test and put those things in. And then what I'm asking you to do is say, explain to me what your outcome means. That may be, the computation part may be easy. Explaining it will be harder, but that's why I want you to do it. I want you to try and explain, what does it mean? What I'm trying to do here is get you to use the language, because I think that ultimately would be very helpful to you. And that's it for today.